In this video, we're going to go through the proofs for the inverse trigonometric function derivatives, and this is going to require a little bit of memory from your trig classes, so let's give it a try. A little bit from algebra too. All right, so if you have y is equal to the inverse sine of x, right, and the domain for this is minus pi over 2 to x pi over 2. Right, then you can use the concept of the inverses from college algebra and say, therefore, sine of y must be equal to x if these are inverses. And the domains and the ranges switch, right? So now we have minus pi over 2 is less than or equal to y is less than or equal to pi over 2, right? Now, so let's take the derivative with respect to x of this sine y equals x. So the derivative with respect to x of sine y and the derivative with respect to x of x is you would have cosine y dy dx equals 1, right? And we're solving for dy dx. So dy dx is 1 over cosine y. All right. Now we're going to wander off over here for a minute. And someone way back yonder, way before my time, okay, said, you know what? We can sit here and remember how you have cosine squared theta plus sine squared theta is equal to 1. And if you put y in there, you could solve for cosine squared y is 1 minus sine squared y. And then you get square root both sides. All right, now since we're looking at minus pi over 2 to pi over 2, remember that in trig world, okay, 1, 2, 3, 4, cosine is positive in quadrants 1 and 4, which is in here. It's this section right in here. All right, so what I want is the positive version, not the negative. I'm trying to narrow it down to where I don't have two possibilities, right? So I just have this one possibility now since I know I'm in the two quadrants where where cosine is positive. All right, now, so going back over to here, we would have dy dx is 1 over the square root of 1 minus sine squared y. But that doesn't look exactly like what we have in our formulas, right? So if you go back up here, we have x is equal to sine of y. So since x is equal to sine y, and you replace that in there, you'd have 1 over 1 minus x squared. And that was the formula that we were used to. Okay, let's do another one. So if y is equal to the inverse cosine of x, and the domain for this is 0 is less than or equal, well, I guess actually we're not talking about the domain. Y is less than or equal to pi. Then cosine y would be equal to x because they're inverses. We can take the derivative with respect to x on both sides. So I would have the negative sine of y dy dx equals 1. So dy dx is 1 over sine y negative. And we know that sine squared y is equal to 1 minus cosine squared y. And sine y is equal to plus or minus the square root of 1 minus cosine squared y. And since we're in quadrants 1 and 2, then we're going to pick the positive version because sine is positive in quadrants 1 and 2. So dy dx is the negative of 1 over 1 minus cosine squared y square root. Okay, but we also know that cosine y is equal to x from above. So it's minus 1 over square root 1 minus x squared after you substitute this in. Not too bad. Okay. All right. Let's try another one. So y is the inverse tangent of x, right? Which is the tangent y equals x. And we're going to do the same process we've been doing. We're going to take the derivative with respect to x. So we would have secant squared y dy dx is equal to 1. So dy dx is equal to 1 over secant squared y, right? Now, we know, from this cosine squared theta plus sine squared theta is equal to 1, that we can divide through by cosine squared theta and have 1 plus tangent squared theta is equal to secant squared theta. And so I'm looking for secant squared y, right? So this is 1 over 1 plus tangent squared y. Now, I didn't have to square root anybody, so I don't have to decide about plus or minus or anything because I'm not square rooting. Those squares are not doing too good copying through. Dy dx. And we know that tangent y from up here, tangent y is equal to x. So dy dx is equal to 1 over 1 plus x squared. I think that's the most straightforward one so far. So y is equal to the inverse cotangent of x implies that the cotangent of y equals x. We take the derivative with respect to x of both sides. So you'd have minus cosecant squared y dy dx is equal to 1. I think you probably got the pattern by now. So dy dx is minus 1 over cosecant squared y. And we know from that cosine squared theta plus sine squared theta equals 1 that we can say that cotangent squared theta plus 1 equals cosecant squared theta. So cosecant squared theta is cotangent squared y. It's y's instead of theta. Sorry, over here it's thetas. And I know that cotangent y is equal to x from above. So it's minus 1 over x squared plus 1. Two more to go. Y is equal to the inverse secant of x. So secant y is equal to x. Take the derivative with respect to x on both sides. And we'd have secant y tangent y dy dx equals 1. So dy dx is equal to 1 over secant y tangent y. Right. And so we know that tangent y is equal to secant squared y minus 1 square root, right? And tangent y is greater than 0, so we know that we want the positive version. So this is 1 over secant y square root of secant squared y minus 1. So it's 1 over, and we have secant y is equal to x from above. So it's 1 over x square root of x squared minus 1. One last one to go. Almost there. So y is equal to cosecant, the inverse cosecant of x implies that cosecant of y is equal to x. Take the derivative with respect to x on both sides. You could probably write the script for this all by yourself. dy dx equals 1. Solve for dy dx. Okay. And then we know that cosecant y is the square root of cosecant squared y minus 1. And so we have minus 1 over x square root of x squared minus 1, because up here we have cosecant y is equal to x, and we substitute that in. And this is dy dx. So surprisingly, that only took us under 13 minutes to get all those proofs done. So if you have to do one for a test or something, it should be fairly quick. And if nothing else like that happens, it does help to know these are not just made up out of thin air, and that there really is a mathematical basis to how these works. How these work. And so I hope to see you at the next video, and look at the little end card, and like and subscribe would be very helpful. Thanks.